Hi everyone. In this class, we are going to learn about the hybridization. I'm going to explain sp2 hybridization, sp3 hybridization, and sp hybridization by taking other examples. Okay, smart big compounds I'm going to take here, and with that I'm going to explain the sp3 hybridization and the sp2 hybridization and sp hybridization, sp hybridization. Hybridization in other compounds. By taking some other examples, I'm going to explain the sp2, sp3, and sp hybridization. Okay. First, I'll go with a sp3 hybridization. sp3 hybridization. So I'll explain this sp3 hybridization by taking example of molecule of formula C2H6. C2H6. So is the molecular formula of the compound, that is ethane. Is the ethane molecule. Ethane molecule. Okay. So by taking this example, I'm going to explain the sp3 hybridization. Okay. So in this molecule, there are two single atoms are there, two carbon atoms are there. Two carbon atoms will act as a central atoms. Okay. So two carbon atoms. Okay. In each carbon, atomic number 6, and its excited state electronic configuration is like this: 1s2, 2s1, and 2p3. So this is I'm writing directly the excited state electronic configuration. Okay, the 2s, the 2px, and 2py and 2pz. Okay, 2pz. There is one electron in the one half electron in the half electron in each orbital, outer shell orbital. Okay. So there are two central atoms, same. Both the central atoms are carbons only. Okay. So they have a same electronic, this type of electronic configuration. The excited state electronic configuration. The excited state electronic configuration. Electronic configuration. Okay. Now, and each carbon, from the each carbon, one s orbital and 3 p orbitals involves in hybridization and give a 4 equivalent sp3 hybrid orbitals. They give a 4 equivalent sp3 hybrid orbitals. Okay. And these 4 sp3 orbitals will surround around each carbon. So in this molecule, there are two central atoms in it. So these 4 sp3 hybrid orbitals will surround the central atom carbon. Okay. So they will be surround like this. Each one are sp3 hybrid orbital. Same way. The carbon 1, the carbon number 1, the carbon 2. Okay. So here also same 4 sp3 hybrid orbitals will orient around the central atom carbon. Okay, this is the sp3 hybrid orbitals. Okay. So from the carbon 1, out of 4 sp3 hybrid orbital, so 1 will overlap with the other sp3 hybrid orbital of carbon. Okay. So this will overlap by n on n. Okay. Will give a sp3 sigma bond. Give a sp3 sigma bond. Okay. Out of 4 from each carbon, one sp3 hybrid orbital overlap with other sp3 hybrid orbital of carbon will give a one sigma bond. Will give a sigma bond. And the remaining sp3 hybrid orbitals will overlap with the s orbital of hydrogen. Will overlap with the s orbital of hydrogen. S orbital of hydrogen. Okay, here we have hydrogen, overlap with the s orbital of hydrogen. The one sp3 overlap with the hydrogen s orbital. Okay, Here also overlap with the s orbital of hydrogen. Okay, so we know well hydrogen atomic number 1, its electronic configuration 1s1. Okay, there is only one electron in the outer shell of this hydrogen. Okay, overlap this. So remain same way. Remaining 3 here also, remaining orbitals overlap with the s orbital of hydrogen. S orbital of sp3, sp3, s overlap. Okay, of hydrogen. Okay. So already we know each sp3 hybrid orbital they have one electron pair, one electron on each. There is one half electron there. Okay. In the hydrogen also, in the hydrogen s orbital also there is one half electron. Okay. So they will pair up with the opposite spin. They will be pair up with the opposite spin. This electron will be paired up with the opposite spin. Here also, they will be paired up with the opposite spin here. So this is one electron of hydrogen and one electron of carbon. Okay. So, but here the both electrons from the carbon, from the other carbons. Okay. So by this way, we'll get a. So here each carbon is sp3 hybridized. Okay. So if you see the structure between the carbons, there is sigma bond there. Is formed by the sp3 and sp3 overlapping, and the remaining 3 sigma bonds are between the hydrogen and carbon, between the carbon and hydrogen, and these are formed by the overlapping of sp3 and s sp3 and s overlapping sp3 of carbon and s of the hydrogen. Okay. Same here also. Here you can see the 3 bonds with the hydrogens. Each are the sigma bonds. These are formed by the overlapping of sp3 and s overlapping. sp3 and s overlapping. Now, so in this compound, the carbon-carbon bond length. Okay, this is the structure. In this compound, the carbon-carbon bond length. Okay, this is the single bond here. This is the single bond. That is a single covalent bond. Okay, so this bond length is 1.54 angstroms, or we'll write as a 1.154 picometers. 154 picometers. Okay, and if you see the carbon hydrogen bond length, if you see the carbon hydrogen bond length, that is around 109 picometers. Okay, this bond length. Okay, the single bond carbon hydrogen bond length is 109 picometers. Okay, so this is about the hybridization other compounds, sp3 hybridization other compounds. Okay, now same way, if you see the sp2 hybridization, for explaining sp2 hybridization, I am taking the molecule that is C2H4. This is the ethene molecule. This is the ethene molecule. Okay. Here also we have 2 carbon central atoms are there. Okay. They'll possess same excited state electronic configuration. Okay. But in this case, in case of sp2 hybridization, so each from each carbon, sp2, 1s2, 1s2, 2s1, and 2p3. Okay. One electron. Okay. For getting the sp2 hybridization, one s orbital, and 2p. That is a 2px, 2py, and 2pz. Okay. One s orbital, 2s orbital, one 2px orbital, and one 2py orbital. So these 3 involves in the hybridization, and we will give a 3 equivalent sp2 hybrid orbitals. They will give a 3 equivalent sp2 hybrid orbitals. And there is one unhybrid orbital. That is, so in this case, there is one unhybrid orbital, that is 2pz. This 2pz is a unhybridized orbital. Unhybridized orbital. There is one unhybridized orbital. Okay. So remaining orbital then one the hybridization. Okay. And this, if you see this, around each carbon, around each carbon, you can see the three, sp2 orbital. So here one sp2 orbital, and here one sp2 orbital, and here one sp2 orbital. Okay. So along that there is one, here are sp2 orbitals. This is sp2 orbital. This is also sp2 orbital. Okay. So along this sp2 orbital there is one unhybrid orbital is there, that is 2pz. So this 2pz will have a dumbbell shape that will be oriented like this. This is the This is the 2pz orbital. This is 2pz orbital with the dumbbell shape. Okay. So in each orbital there is one unpaired electron there, one half electron there. In the hybrid orbitals at the same time, in unhybrid orbital also there is one unpaired electron. Okay. Same here also. Around the second carbon 1, carbon 2. Here also there is the same number. Okay. You can see the one. This is the one sp2. This is also one sp2. These are the sp2 orbitals. These are sp2 orbital. So along that there is a unhybridized 2pz orbital. Okay. And all orbitals they have a one half electron there. One half electron there. Okay. Now, so this sp2 orbital of the carbons, they overlap by end on end and will give a one sigma bond. Remaining sp2 orbital overlap with the s orbital of hydrogen. S orbital of hydrogen. This also overlap with the s orbital of hydrogen. Okay. Here also this other carbons. So this also overlap with the s orbital of hydrogen. This also overlap with the s orbital of hydrogen. Okay. So all will give a sigma bond. Okay. And while overlapping, electron get paired up with opposite spin. Okay. Electron get paired up with the opposite spin. Okay. So sp2 and s orbital overlap, by that we get a one sigma bond. Carbon, hydrogen, sigma bonds we got. Okay. Now, same way there is one unhybrid orbital there. Okay. They also have unpaired electrons there. Okay. So this unhybrid orbital, that is 2pz will overlap side by side. This will overlap by side by side. Okay. 2pz and 2pz of other carbons, they will overlap by side by side, and give a pi bond. They give a pi bond. Okay. So the other way bonding will happens in the ethene molecule when the central atom process sp2 hybridization. Okay. If you see here, there is a carbon-carbon single bond, sigma bond. This is formed by the sp2 and sp2 overlapping. Okay. So along that, there is electron cloud, pi electron cloud. Pi electron cloud is it. So above the sigma bond and below the sigma bond. Okay. The pi electron cloud. Okay. And remaining a carbon hydrogen, sigma bond. Is the carbon hydrogen sigma bond. Same here also carbon hydrogen sigma bond. Okay. This carbon hydrogen sigma bond formed by the sp2 and s overlapping of the hydrogen. Okay. And finally, if you draw the structure, there is a double bond in the carbon and carbon, and there is single covalent between the carbon and hydrogen. Okay. Out of the double bond, one is the covalent, one is the sigma covalent bond, one is the pi covalent bond. Okay. So due to the pi covalent bond, the bond length will be decreases as compared to the single covalent bond. So before there is a much bond length there. So 154 picometers. Now it is reached to the 134 picometers. The carbon double bond length. Okay. So the length will be decreases. Okay. And the same way, the carbon hydrogen bond length also will decreases to the 108 picometers. Okay. So always the carbon, if the carbon is sp2, if it is bond, sp2 carbon hydrogen bond length is the bond length 108 picometers. Okay. And here you can see the two types of bond angles. Okay. So between here you can see the 117.6 is the bond angle here between the carbon and between the hydrogen hydrogen bond angle is 117.6 degree. And if you see the carbon hydrogen, here you can see the bond angle is around 121 degrees. 121 degrees. Okay. So between carbon hydrogen bond angle is 121 degree. Hydrogen hydrogen bond angle is 117.6 degrees. Is the bond angle. Okay. So the about sp2 hybridization in the case of molecule of ethene molecule. Ethene molecule. Now, same way, if you see the sp2 hybridization, sp2 hybridization, sp2 hybridization. If you see the sp2 hybridization, in this case, sorry, sp hybridization. If you see the sp hybridization, so if you see the sp hybridization, so here I am taking the example of molecule that is C2H2. The molecule name is ethyne molecule. Ethyne molecule. Okay. So here also you have a two carbon central carbons are there. So each one have the same this type of electronic configuration. Okay. To get a sp2 hybridization, one s orbital and one s orbital, one p orbitals. So these two involved in the hybridization, one 2s orbital and 2p x orbital. So involves in hybridization will give a 2 sp hybrid orbital. Give a 2 sp hybrid orbitals. Okay. Now, so along that we have a 2 unhybrid orbitals. These two are the unhybridized orbitals. Okay, and these orbitals will orient along the central carbons. You see here how they will orient. Okay. Around each carbon there are two sp orbitals. So here you have in this molecule they are simple atom. Around each carbon there are two sp orbitals. Here also you can see them two sp orbitals here. This is the two sp orbitals. So along that you can see this is one sp and this is one sp. Okay. Along that you can see the two unhybrid orbitals, 2px, 2px. Okay. They will possess a dumbbell shape. So there will be, so here one is the 2p, the 2py. At the same time, you can see the 2pz also. These are 2pz. Okay, here also you can see the 2py, the 2py. Here are 2pz orbital. These are 2pz orbital. Okay. So every orbital have a one half-fill electron in them. Okay. Now, so here, so there is every orbital have a one electron, one half-fill electron there. They have one half-fill electron. They have one half-fill electron there. Here. Okay. Now, and here, this sp and sp of two carbons. Okay. So they overlap end on end. They give one sigma bond by the sp overlapping. And remaining sp orbitals overlap with the s orbital of hydrogen. It's also overlap with the s orbital of hydrogen, and the electrons will get paired up. Okay, here also the electron will get paired up. Electron will get paired up with opposite spin. Okay, so this also will give a sigma bond. So here one sigma bond. This is one sigma bond. SPS sigma bond. Okay, so remaining two unhybrid orbitals, they involve in the side by side overlapping. Okay, 2px, 2py and 2py. 2py and 2py. These are 2py and these are 2py. So they overlap side by side, overlap by side, will cause us one pi bond. Okay. Same way, another 2pz and 2pz, they also overlap by side, will give a one more pi bond, one more pi bond. Okay. So in this molecule, you can see the pi electron cloud on the sigma carbon sigma bond. Okay, the carbon sigma bond. So top one pi bond, bottom one pi bond, and also carbon hydrogen sigma bond. Okay, so here you can see the two pi bonds. Now if you see the bond angle and bond lengths. Okay, carbon triple bond length is 121 picometers, and carbon hydrogen bond length is around 105 picometers, and the bond angle is 180 degrees. The bond angle is 180 degrees. Carbon hydrogen bond is 180 degrees with a bond angle. Okay. Now see here. So the carbon hydrogen bond length is decreasing. So that means carbon hydrogen bond length depends upon the hybridization of the central carbon. Okay. So in the case of sp3 and sp3 carbon and hydrogen, the bond length is around 109. You see the sp2 carbon and hydrogen bond length is 108 picometers, not 8 picometers. Same way, sp carbon and hydrogen bond length is 105 picometers with a variation. With a variation of the bond. Now, at the same time, carbon single bond length is 154 picometers. Carbon double bond length is 134 picometers. Carbon triple bond length is 121 picometers. With a variation in the carbon bond length also. That depends upon the hybridization of the carbons. Okay. So this is about the hybridations. sp3 hybridization, sp2 and sp hybridization in other compounds. Okay. Thank you. Have a nice day.